Hello, geometry. Welcome to lesson 10 for an inscribed angles. This is a big lesson with circles. The state test loves inscribed angles. Bound to have at least one or two questions on the state test. Now, before we get into inscribed angles, let's remember what a central angle is, right? So if I have a circle with center P, and I have two radii, say AP and BP, right? This angle right here is what we call a central angle. Right, that's a central angle. It's a central angle because its vertex is the center. The measure of the central angle is equal to the measure of its intercepted arc. So AB is that arc that you're intercepting. So the measure of angle APB is equal to the measure of arc AB. So keep that in mind as we go through today and talk about inscribed angles, right? Because we will use that to help us with inscribed angles. All right, so it says, what is the relationship between arc AB and angle ACB? So notice angle ACB has its vertex on the circle. This is what's called an inscribed angle. An inscribed angle has its vertex on the circle, right? So let's go through and try to understand how to find the measure of this angle and how it compares to arc AB. Now, this is going to be an algebraic proof. All right. And again, I can't emphasize enough that this word inscribed means that the vertex is on circle. So vertex on the circle. All right, so let's take a look here. And let's first start with the central angle, right? So you notice how we have the center drawn. Let's draw in radius BQ. So now we have a central angle, angle AQB, right? It's going to be equal to its intercepted arc. So we know that the measure of angle AQB is equal to the measure of arc AB, right? Again, that's because it's a central angle. Central angle. Okay. Now, what we did here is we just created a triangle over here. We created triangle BCQ or QBC, right? This central angle right here is also an exterior angle to triangle BQC. So this extra angle is going to be equal to the sum of angles B and C. So we also know that the measure of angle AQB is equal to the sum of angle B plus angle C. Again, this is called the triangle exterior angle theorem. We learned this back in topic 2 or 4. And we talked about, I think it was topic 2. Yeah, so way long ago. Okay, now, because we drew in BQ as a radius, we also know that this radius is congruent to QC, which is a radius. This means that QBC is an isosceles triangle. And if QBC is an isosceles triangle, if it has two congruent sides, it has two congruent angles, which would be angle B and angle C. So we know that the I'm going to just do quickly. The measure of angle B is equal to the measure of angle C. I'm skipping steps, right? This is the isosceles triangle theorem, which says they're congruent. So if the angles are congruent, then the measures are equal. Again, I skipped a step. Sorry about that. Hope you're okay. But again, why is this? This is because they're both radii. So now we can do a substitution, right? If we know that B and C are equal, we can take out the B's because we don't care about the B's, right? This angle right here is the same as angle C. Right, vertex, angle C. We care about angle C. So let's take out B and let's put C, which would give us two C's. So the measure of angle AQB is equal to 2 measure of angle C's. And that's substitution. Well, we know that because of this first step, the measure of the central angle is equal to the arc. So we know that the measure of arc AB is now going to be 2 measures of angle C, and that is again by substitution. And how do you get rid of this 2? You divide by 2 or multiply by 1/2. So if you multiply both sides by 1/2, you get 1/2. The measure of arc AB equals the measure of angle C. And this is by division, property of equality. And there you have it, folks. We just proved that this inscribed angle, angle ACB, or angle C, is equal to half of its intercepted arc AB. This is the big idea. Inscribed angle is half its arc. I have it written right down here. right here. The measure of an inscribed angle is half the arc. Inscribed angle is half the arc. Now, sometimes you're given the arc and you're looking for the inscribed angle, which would be good here because you plug in the arc measure, take half it. Other times you're looking for the arc measure. So if the inscribed angle is half the arc, then if I'm looking for the measure of the arc, it's going to be 2 times the measure of the inscribed angle. So keep that in mind too. If I'm looking for the measure of the arc, you should take the angle and multiply it by 2. All good stuff here, right? This is how an inscribed angle is used to find an arc and vice versa. Okay, oh, sorry. Now, when you talk about the inscribed angle theorem, we did case 1, right? Case 1 where we had a diameter drawn. We had that one segment going through the diameter, right? But there are actually 3 cases for the inscribed angle theorem. No matter how you slice it, though, no matter what case you're looking at, whether the center's on a side of the angle, whether the center's inside the angle, whether the center's outside, no matter what you do, if angle S has its vertex on the circle and it intercepts arc RT, then the measure of the angle is half of the arc. All right, so let's use this tool here. Let's go to Savis. I think it says we can move all the points around. I think it does. I think I can. There we go. There's our thinking bubbles. Okay, so again, notice that the first inscribed angle is 45 and its arc is 90, right? And again, 90 to 45, 1/2 times 2. If we move R, right, we make that inscribed angle bigger. Notice that the relationship still holds true, right? If you move S to make the circle bigger, it doesn't matter about the actual length. Again, the measures are proportional, right? Okay, so there we go. All right, so we're going to do, I think, 1, 2, 3 problems on this video, and then we'll stop the video. Okay, all right, so next problem here, or first problem, I should say. Okay, so they give us the measure of arc DG is 45.6, pretty specific, right? So the measure of arc DG, so this arc right here, is 45.6 degrees. We want to know what are the measures of angle E and F. Well, if you look at angle E, first of all, angle E's vertex is on the circle, right? So, and so is F's. So these are both inscribed angles, which means they equal half the arc, right? So if we take E and trace its side, so angle E goes to D and angle E goes to G, notice that the intercepted arc of angle E is DG. So the measure of angle E is going to be 1/2 the measure of arc DG, which is just 1/2 45.6. And half of 45.6 is 22.8 degrees. If we take a look at F and trace it, it also intercepts the same exact arc. The measure of angle F is also going to be half of the measure of arc DG, which is going to be 22.8 degrees as well. So in this picture, actually, angle E and angle F are congruent because they intercept the same arc. That is going to be a corollary you see in a minute. Okay, next one. If arc RT is a semicircle, what is the measure of angle RST? So now we have this RT, and again, we're going to use this RT over here. They really should have used 3 letters, but so this RT is a semicircle, right? If RT is a semicircle, then it means that this arc measures 180 because it's half of 360, okay? This arc. Now understand that segment RT goes through Q. Segment RT is a diameter. It's very important that when you deal with circles, if you see a radius or diameter, you identify it, right? So measure or angle RST, vertex is S, is on the circle. So I use blue. So because S is on the circle, this is an inscribed angle, which means it's half of its arc. Okay. So if we trace Notice that the endpoints of angle RST are the endpoints of a diameter. So therefore, the measure of angle RST is going to be half the measure of arc RT, which is a semicircle, which means it'll be half of 180, which is 90 degrees. And that means that this angle that intercepts a semicircle is going to be a right angle. Okay, and that's going to be another corollary you see. All right, and last but not least, so here you go. It says if the measure of arc ABC is 184 and the measure of arc BCD is 242, what are the measures of the angles of quadrilateral ABC? So a little bit more involved here. So if I take ABC, which is this arc here, and I'll use blue, ABC, so that is 184 degrees. And then I take BCD, so there's some overlap, right? BCD, right? And that is 242. And they want to know what are the measures of the angles of this quadrilateral. So right now we can find two angle measures in this quadrilateral, right? If we look at arc ABC, right? It ends at A and ends at C. Let's drag those points down to a common third point. If we drag A down to D, C down to D, that means that angle ADC is the inscribed angle that intercepts arc ABC. That means that the measure of angle ADC will be half the measure of arc ABC. Right? Well, that's going to be half of 184, which is going to be 92 degrees. So angle ADC, this angle is 92 degrees. Using the blue arc BCD, if we trace back B, we can trace it back to A, trace D back to A. This means that angle BAD is the inscribed angle that intercepts arc BCD. So the measure of angle BAD will be half the measure of arc BCD. That means it'll be half of 242, and that'll be 121 degrees. So that was given to us, yes? Well, now we have to use some subtraction to find the other two arcs in this problem, right? ABC is the red arc. I'm going to counter it with the purple arc, right? That would be arc ADC. So to find the measure of arc ADC, right? ABC, the red arc, and ADC, the purple arc, make the circle. That would be 360 degrees. And let's subtract ABC from that. ABC was 184. So that's going to be 176. So this purple arc is 176 degrees, right? If you go from A to C and you trace back, it lands, or they connect at point D. So the measure of angle ABC will be half the measure of arc ADC. That'll be half of 176. And half of 176 will be 88 degrees. So angle B is 88 degrees. Now I want to make a mention. If you compare angle D and angle B, they're called opposite angles because they're across the figure, they're not next. Notice that 92 and 88, if you add them, they equal 180. That's an important idea. Okay, kind of jumping the gun, but it is. Now I did not, let me put the blue angle measure, angle A. This is 121 degrees. So now let's do the same thing to find C. I'm going to use green, right? So angle C opens up to arc BAD, which I do not have yet, right? But BAD and the blue arc BCD make the circle. So to find the measure of, not angle, to find the measure of arc, BAD, I'm going to take 360 and subtract arc BCD, which was 242, the blue arc. And that's going to be 118 degrees. So this green arc is 108 degrees, 118 degrees. So now to find the measure of angle BCD, angle C, you're going to take half the measure of arc BAD. That's half of 118, and that's going to be 59 degrees. So this is 59 degrees. And again, if you look diagonally, 121 and 59, if you add them together, they're going to add up to 180 degrees. which again is going to be an idea we talk about as a corollary. And there's your 1, 2, 3, 4 angle measures. Also, if you add them up, you'll get 360, which should also count. Okay. I did not mention that this is an inscribed quadrilateral. Notice that A, B, C, and D are all on the circle, and again, that's why we did inscribed angles. All right, so I'm going to stop this video now. The next video will start with the explanation or the formal introduction of these three corollaries, and then we'll do some more problems.